March 1944, Rechlin Air Base, Germany. Three Luftwaffe engineers pry open the cockpit of a captured P-47 Thunderbolt, expecting to find something comparable to their own fighters. What they saw left them paralyzed. 6 tons. The aircraft weighed 6 tons fully loaded, twice that of a Messerschmitt Bf-109, and yet it flew. It maneuvered. It dominated European skies. According to all German aeronautical design doctrine, this machine should have fallen from the sky under its own weight. But it didn't. And this impossible paradox would reveal a devastating truth that would change everything they understood about war engineering. Oberingenieur Klaus Hartmann, head of the Technical Analysis Division at Rechlin, had inspected dozens of captured Allied aircraft, Spitfires, Mustangs, B-17s. Each brought revelations, of course, but always within the bounds of conventional understanding. More powerful engines here, thicker armor there. Competent engineering executed with abundant resources. Nothing that challenged the fundamentals. But when Hartmann's team removed the access panels from the P-47 that cold spring morning, the silence that followed wasn't one of technical concentration. It was incomprehension, silent shock in the face of a reality that shouldn't exist. "This can't fly," muttered Friedrich Weber, an aeronautical engineer with 15 years of experience in Focke-Wulf projects. He wasn't being sarcastic. He was genuinely confused. The weight, the complexity, the brutal size of each component. But it didn't just fly, it dominated. And the combat numbers proved it brutally. Combat reports had already painted a troubling picture. P-47s absorbing damage that would destroy any German fighter. P-47s carrying bomb loads equivalent to medium bombers. P-47s diving at speeds that tore the wings off Messerschmitts and Focke-Wulfs. Terminal velocity, over 500 miles per hour. Dive limit, practically non-existent. But numbers on paper are one thing. Seeing the physical machine, touching its systems, mapping its internal architecture, that was an entirely different dimension of reality. But then Weber picked up the specifications clipboard, and the first line made him stop. 6 tons fully loaded. He checked again, certain he had misread. There was no mistake. The Messerschmitt Bf-109G, workhorse of the Luftwaffe, weighed 3 tons. The Focke-Wulf FW-190A, their most robust fighter, weighed 4. The P-47 weighed twice as much as the 109. And yet it flew, maneuvered, fought, won. How? The first anomaly that confronted Hartmann's team was the armament. 8 50 caliber Browning machine guns. 8, each fed by 400 rounds. Total 3,200 bullets. By comparison, a typical Bf-109G6 carried one 20mm MG-151 cannon with 200 rounds and two 13mm MG-131 machine guns with 600 rounds each. Total 1,400 bullets, less than half the P-47's ammunition. But it wasn't just quantity, it was philosophy. The Germans had optimized for precision and stopping power, large caliber cannons, lower rate of fire, smaller ammunition load. The theory was elegant, every shot must count. Efficiency through precision. The Americans had chosen a radically different path, absolutely overwhelming volume of fire. 8 converging streams of 50 caliber projectiles, each with a muzzle velocity of 2,900 feet per second. When a P-47 opened fire, it wasn't aiming at a point. It was creating a zone of destruction. A cone of metal slicing through space at 10,000 combined rounds per minute. Weber did the calculations quickly. In a 2-second burst, this aircraft dumps more than 300 rounds. Our 109 would fire about 30. Pause as silence as the implications settled in. They're not trying to hit the enemy. They're trying to fill the volume of space where the enemy exists. It was a crucial distinction, and it revealed something fundamental about the American design mentality. Redundancy, not as optimization failure, but as deliberate strategy. The armor confirmed this philosophy. The P-47's cockpit was protected by hardened steel plates, totaling over 600 pounds. 600 pounds dedicated exclusively to keeping the pilot alive. 2-inch thick armored glass behind the pilot's head. Armor plates under the seat. Plates protecting critical hydraulic systems. By contrast, a typical Bf-109G carried about 175 pounds of armor, a third of the American protection. German engineers had made choices. Every pound of dead weight meant compromised performance, reduced speed, diminished maneuverability. lower service ceiling. The Americans apparently didn't care about these trade-offs, or more precisely, they had decided that pilot survival was worth any cost in performance. "Observe this," said Hartmann, pointing to the fuel tanks. They were self-sealing, coated with multiple layers of synthetic rubber that, when punctured by projectiles, chemically expanded to close the hole. More weight, more complexity, more cost. But also, pilots returning home instead of burning in crashes over hostile territory. Each system the team examined revealed the same priority: robustness over elegance, redundancy over efficiency, survival over optimization. And then they reached the engine. The Pratt & Whitney R2800 Double Wasp was a monster. 18 cylinders arranged in 2 radial rows of 9 cylinders each. Displacement, 2,800 cubic inches. For context, the BMW 801 that powered the FW190 displaced 2,560 cubic inches and was already considered enormous by European standards. But it wasn't the size that shocked Hartmann. It was the power. The R2800 delivered 2,000 horsepower at sea level, with the water methanol injection system activated. Water methanol. It could exceed 2,300 horsepower for short periods. 2,300 horsepower, Weber repeated, incredulous. Our BMW 801D produces 1,700 horsepower. The Daimler-Benz DB605 in the 109 delivers 1,475 horsepower. He paused. They have 50 to 60% more power available, but the most devastating realization didn't come from raw power. It came from durability. Hartmann discovered maintenance records captured along with the aircraft. The R2800 engine had a designed service life of 1,000 hours between major overhauls. 1,000 hours. The most advanced German engines rarely exceeded 300 hours before requiring complete rebuilding. It wasn't just superior engineering. It was engineering of a different order of magnitude. How do they achieve this? Asked Weber, examining the forged cylinders, the nickel-chromium valves, the precision bearings. Metallurgy? Manufacturing processes? Tolerances? Hartmann shook his head slowly. All of that, but mainly resources. They can use the best available alloys. They can test to destruction and redesign. They can produce components with tolerances that would require our entire annual production of precision tooling for just one of their factories. It was a bitter truth. Germany was fighting a war of limited resources. Every gram of rare metal, every hour of machine time, every technical specialist was precious. Optimization wasn't a philosophical choice. It was a survival necessity. The Americans didn't have these constraints, or if they did, they were on such a different scale that they could seem unlimited to European observers. The P-47's hydraulic system confirmed this disparity. Operating pressure, 2,000 pounds per square inch. 2,000. German systems operated between 1,000 and 1,200 psi. The American system was redundant. 2 independent hydraulic pumps, backup lines, automatic isolation valves. If one system failed, the other took over instantly. They designed every system assuming it will fail under combat, observed Hartmann, and then designed backups for the backups. It was the antithesis of German engineering. Where the Germans sought perfection through refinement, eliminating failure points through superior design, the Americans sought reliability through redundancy. Assume everything can fail and ensure that failures aren't fatal. It wasn't elegant. It was effective. But perhaps the most disturbing revelation wasn't in any individual system. It was in the integration. Every component of the P-47 was oversized, yes, but they all worked together in a brutal balance. The monstrous engine required a giant propeller, 4 meters in diameter. The giant propeller required long landing gear. The long landing gear required a robust fuselage. The robust fuselage allowed heavy armor. The heavy armor required even more engine power. It was a design cycle that amplified every decision. Not incremental optimization, but systemic amplification. And it worked. By God, it worked frighteningly well. The combat data confirmed it. Kill ratio against BF-109s, 3-to-1 in favor of the P-47. Against FW-190s, 2-to-1. Survival rate after combat damage, 73% for P-47s versus 41% for German fighters in comparable situations. 73%. Nearly 3 out of 4 damaged P-47s made it home. Less than half of damaged German fighters could do the same. Hartmann closed his notebook. 3 days of intensive analysis had produced a technical report of 140 pages, but the conclusion could be summarized in one devastating sentence. The Americans had developed a fundamentally superior aircraft design philosophy for industrial war of attrition. Not smarter, not more refined, but suited for the type of war that was actually being fought. A war where replacement pilots had 50 hours of flight time, where field maintenance happened under bombardment, where survival mattered more than maximum performance. Can we replicate this? Weber asked. The question hung in the cold air of Rechlin. Both knew the answer, but saying it out loud made it all real. No, Hartmann replied. Not with our current industrial base, not with our resource constraints, not in time to make a difference. But there was something more in Hartmann's eyes, a deeper insight that technical numbers couldn't fully capture. Even if we could, he continued slowly, I'm not sure we should, because it would mean admitting that our entire approach was wrong from the beginning. That elegance and efficiency don't win modern industrial wars. That brutal redundancy and overwhelming power do. It was a bitter pill to swallow for men trained to see engineering as the art of doing more with less. But the real shock was yet to come, because when they examined the flight systems, the instruments, the controls, when they delved into the interface between pilot and machine, they discovered something even more disturbing about the American philosophy of war design. Let's examine what they found, system by system. The first shock came in the flight controls. German engineers were accustomed to traditional cable and rod systems, mechanically simple, reliable, combat-tested. Opening the P-47's access panels, they found something completely different. Hydraulic systems, pressure-assisted controls, control surfaces that responded with a precision that defied physics. And here's what that meant in actual combat. IBF-109 or FW-190 in a high-speed dive faced a critical problem. Above 400 miles per hour, the aerodynamic forces on the control surfaces became so intense that the pilot physically struggled with the controls. Cables stretched, rods flexed. Response became sluggish, imprecise. In life-or-death situations, that fraction of a second delay killed. The P-47 dove at over 550 miles per hour, effortlessly. Hydraulic controls meant that the pilot's physical strength no longer limited maneuverability. Oil pressure did the heavy lifting. The pilot simply guided. No delay, no resistance, no physical struggle while 50 caliber machine guns tracked German targets across the sky. Combat records confirmed this brutally. P-47 pilots routinely reported escaping German interceptors through vertical dives that no German fighter dared to follow. Not because the Germans weren't brave, because their aircraft simply couldn't take it. German engineers noted, controls responsive up to speeds that exceed our ability to replicate with current cable systems. But there was more. The engine. The Pratt & Whitney R2800 Double Wasp. 18 cylinders arranged in 2 radial rows. 2,000 horsepower with potential for much more with water injection. For context, the best German inline engines, the Daimler-Benz DB605 in the Bf109G, the BMW 801 radial in the FW190, produced between 1,200 and 1,475 horsepower. Good engines, precision engines, but simply not in the same class. And it wasn't just about raw horsepower. It was about where that power worked best. Altitude, the environment where bomber escort combat actually happened, between 25,000 and 30,000 feet, where B-17 and B-24 bombers flew their missions, where thin air left conventional engines gasping and weak. The P-47 had a turbocharger, not the kind of mechanical supercharger the Germans used. Those worked, but they were driven directly by the engine through gears or belts. Every horsepower used to drive the supercharger was a horsepower stolen from the propeller. Efficient at low altitudes, increasingly inefficient as you climbed, the American turbocharger system was different. Fundamentally different. It ran on exhaust gases. Wasted energy that normally went out the exhaust pipes now spun a turbine. That turbine compressed intake air. The engine breathed dense air even at 40,000 feet, without stealing power from the crankshaft, without parasitic losses. German engineers understood the theory. They had experimented with turbochargers on prototypes. But mass manufacturing, the special metals needed to withstand extreme exhaust temperatures, the precision tolerances necessary to prevent catastrophic failures, the resources and industrial capacity to produce this at scale while also producing tanks, submarines and artillery. Impossible. And the Americans were doing it in every P-47 that rolled off the production line. 15,683 of them, in the end. A German engineer wrote in his report, "The integration of the turbocharger represents advanced manufacturing that our current suppliers cannot replicate under wartime constraints." Translation, we understand how it works, we just can't do it. But what truly left German engineers speechless was the armament. 850 cal Browning machine guns, 4 in each wing, 3,400 rounds of ammunition, all synchronized to converge at a lethal point at 300 yards. Compare that to German fighter armament standards. The Bf-109G typically carried one 20mm cannon through the propeller hub and two 92mm machine guns above the engine. Some variants added 20mm cannons under the wings. Devastating firepower when it hit, but ammunition was limited. Perhaps 60-90 rounds for the 20mm cannons. Maybe 500 rounds for each machine gun. The FW-190 was better armed, with 4 92mm or 13mm machine guns, plus 2 or 4 20mm cannons depending on the variant. But again, limited ammunition, significant weight, aerodynamic drag. The P-47 carried 3,400 rounds, 10 to 15 seconds of continuous fire before running empty. In actual combat practice, that meant 20 to 30 short bursts, opportunity after opportunity to hit targets. Pilots could afford to be generous with ammunition because they had so much. And the ballistics of the 50 cal Browning were perfect for air combat. High muzzle velocity, flat trajectory, sufficient penetration power to pierce cockpit armor at 400 yards, rate of fire fast enough to create a wall of lead. Combat records showed P-47 pilots downing FW-190s with 2-second bursts. The volume of fire compensated for minor aiming imprecisions. 8 converging streams of 50 cal bullets created a kill zone where anything caught inside was destroyed. But there was something more in the German reports, something beyond weapon specifications, survivability. The P-47 had earned the nickname Jug, short for Juggernaut. It wasn't just marketing. It was recognition of a design philosophy that the Germans simply didn't adopt. Pilot armor. Not just a backplate complete armored seat protection wrapping around the pilot. Self-sealing fuel tanks, redundant systems. The entire fuselage designed to absorb damage and keep flying. German fighters followed a different philosophy. Light, agile, fast. Every pound of armor was a pound of lost performance. Fine for homeland defense, where friendly airfields were just minutes away, but the P-47 was designed to escort bombers deep into enemy territory. Survival wasn't a luxury, it was a requirement. Combat reports told impressive stories. P-47s returning to base with engines leaking oil, control surfaces torn by shrapnel, entire wing sections missing, and the pilots alive, unharmed, ready to fly again the next day. A German engineer noted documented cases of P-47s surviving direct hits from 20mm cannon shells that would have downed a Bf-109 instantly. Damage tolerance wasn't an accident. It was intentional engineering. But perhaps the most devastating conclusion wasn't about any individual system. It was about manufacturing. The Germans understood precision engineering. They had to. With limited resources and industrial capacity constantly under bombardment, every component had to be perfect. Rigorous quality control, tight tolerances, high-level craftsmanship. The P-47 represented an entirely different philosophy. Good enough at massive scale. 15,683 P-47s produced during the war, compared to approximately 34,000 Bf-109s of all variants, but the 109 had been in production since 1937. The P-47 entered combat 1943. In just 2 years of heavy combat deployment, American production rivaled German numbers, despite starting much later. And it wasn't just quantity. It was the complexity of what they were mass producing. hydraulic systems that German fighters didn't have, turbochargers that German suppliers couldn't replicate, 8 perfectly synchronized machine guns. All of this mass-produced with consistency that guaranteed reliability. The German engineers grasped the brutal truth. Each system in isolation was impressive. The hydraulic controls alone represented a significant advantage. The turbocharger alone changed high-altitude performance. The armament alone provided superior firepower. But together, they were insurmountable. And the part that kept the engineers awake at night wasn't that they didn't understand how it worked. They understood perfectly. They had dissected every system, documented every innovation, grasped the engineering principles. The problem was that understanding wasn't the same as replicating. Even if they had the resources, the special metals, the precision tools, the manufacturing capacity, the time needed to redesign German fighters with these capabilities, test the new designs, certify them for production, retool factories, train pilots on the new systems. The war would be over before the first production aircraft rolled off the line. And that's assuming the RAF and the USAF stopped bombing their factories, which they wouldn't, especially now with P-47 escorts allowing bombers to penetrate deeper into German territory than ever before. An engineering report to the Luftwaffe High Command summed it up in a single devastating sentence. The P-47 represents not an evolutionary step, but a different approach to air superiority that we cannot replicate under current industrial constraints. It was a confession, an admission, an acknowledgement that American engineering hadn't just caught up. It had surpassed, in ways that couldn't be copied or neutralized through German manufacturing. The engineers compiled their findings, comparative charts showing performance gaps, technical analyses detailing why each system was superior, realistic assessments of how much time and resources would be needed to close the gap. And as they organized the reports, an emotional shift occurred. The initial analytical curiosity, the professional fascination of studying superior engineering, gave way to something darker, strategic dread, because understanding that you can't match the enemy isn't the end of anything. It's the beginning of something completely different. That's the moment when you stop trying to win at their game and start looking for a different game entirely. The question was no longer, how do we make a fighter better than the P-47? The question became, how do we fight something we can't match? And that question, that fundamental shift in German tactical strategy, would reshape the final years of the air war over Europe in ways no one could fully predict. The engineer's report landed on Hermann Göring's desk with a simple and devastating conclusion. The P-47's superiority cannot be neutralized through our current manufacturing capacity. Tactical adjustments are necessary. What happened next would change the Luftwaffe's doctrine for the remainder of the war. When that report finally reached the hands of Hermann Göring, Supreme Commander of the Luftwaffe, the reaction was deafening silence. There were no shouts, no immediate denial, only the crushing weight of technical truth that no ideology could erase. The engineers who witnessed that moment described a palpable transformation. Men who had designed the Focke-Wulf 190s and Messerschmitt 109s, magnificent aircraft in their own right, now faced the reality that their creations operated within limitations that the Americans had simply surpassed. It wasn't a question of intelligence. German engineering remained technically brilliant. It was a question of fundamental philosophy. While the Germans optimized each component to theoretical perfection, the Americans had built a system where individual perfection was sacrificed in favor of collective effectiveness. And that realization spread like wildfire through the Luftwaffe's command centers. Veteran pilots who had faced P-47s in combat finally understood why their attacks so often failed. It wasn't lack of courage or skill. It was brutal mathematics. You cannot consistently shoot down what was designed to absorb punishment that would destroy any other fighter. Squadron commanders began reporting a disturbing phenomenon. Each week, more P-47s appeared in European skies. Not in small numbers, in massive formations that made German numerical superiority a distant memory. American production wasn't just efficient, it was overwhelming. And then came the moment that would define the rest of the air war. In a high-level meeting in mid-1943, Luftwaffe generals confronted the truth their engineers already knew. Air superiority was slipping from their grasp, and there was no viable path to recover it. A veteran pilot, decorated with the Iron Cross, put it in brutally simple terms. "We can shoot down 10 P-47s, and tomorrow there will be 20 in their place. They can lose half their air force and rebuild it in weeks. We lose 10 experienced pilots and it takes us months to replace them, if we can at all." The implication was crystal clear. Germany was fighting a war of industrial attrition against a nation whose production capacity made attrition a suicidal strategy. Engineers who had spent years pursuing technical perfection now processed a devastating realization. They had optimized for the wrong problem. While they created masterpieces of aeronautical engineering, the Americans had solved the problem of war. And war is not won by the most elegant machine, but by the machine that can be everywhere, protecting every bomber every day. The Luftwaffe's response was a series of tactical adjustments born of desperation and realism. First change: abandonment of offensive doctrine. Fighter squadrons that once aggressively patrolled the skies hunting for targets now adopted defensive postures, carefully choosing when and where to engage. It wasn't cowardice, it was preservation of irreplaceable resources. Second change: accelerated development of specialized armaments. If they couldn't match the P-47's robustness, perhaps they could develop cannons and rockets that would overcome that armor. Prototypes were rushed, tests were compressed, but every technical solution ran into the same barrier: production at scale. Third change: reconfiguration of industrial priorities. Resources were diverted from long-term development projects to immediate production of defensive fighters. It was a tacit admission that the air war had become a battle for survival, not for victory. And through it all, the P-47s kept coming. Hundreds became thousands. Thousands became a constant and inescapable presence in European skies. The numbers tell a devastating story. In 1943, before the massive proliferation of P-47s as bomber escorts, Allied bomber loss rates on deep missions over Germany frequently exceeded 10%, and in some catastrophic missions surpassed 20%. In 1944, with P-47s providing long-range escort, those rates plummeted. Missions that were once nearly suicidal became operationally viable. Bombers reached targets deep in industrial Germany, with losses that, while still significant, were sustainable. Allied air superiority was not won in a single epic battle. It was a gradual and relentless erosion, measured in accumulated sorties, in protected flight hours, in bombers that returned to fly again. Military historians identify a clear turning point. Between late 1943 and mid-1944, the Luftwaffe transitioned from an offensive force capable of contesting airspace to a defensive force struggling to protect its own territory. And the P-47 was one of the primary instruments of that transformation. The German industry, already overwhelmed by multiple war fronts, simply couldn't close the gap. Every aircraft factory that could produce fighters was under constant threat of bombing. Every production line that reached maximum efficiency faced shortages of critical raw materials. American industrial superiority wasn't just quantitative, it was systemic. And the German engineers, those who had begun this story examining a captured P-47 with a mixture of admiration and horror, now faced the legacy of their design choices. They had created engineering marvels. The Focke-Wulf 190 remains to this day recognized as one of the most elegantly designed fighters of World War II. The Messerschmitt 262, the first operational jet fighter, was a breathtaking technological leap. But individual marvels don't win industrial wars, and that's the deepest and most enduring lesson of this story. The American engineering philosophy, pragmatic, focused on scale, willing to accept good enough in individual components to achieve systemic excellence, would prove to be not only effective during the war, but influential for decades afterward. When the Cold War began, and new generations of military aircraft were designed, engineers on both sides of the Atlantic carried the lessons of the P-47. The Soviet Union, observing both American successes and German failures, adopted mass production philosophies that echoed the Thunderbolt's principles: robustness, maintenance, simplicity, scalability. America itself continued refining this approach. The F-4 Phantom, one of the most prolific Cold War fighters, carried direct conceptual DNA from the P-47: raw power, impressive payload capacity, extraordinary survivability, and above all, producibility in numbers that guaranteed massive operational presence. The lesson wasn't that technical perfection was undesirable. It was that technical perfection without strategic context is a luxury that industrial wars don't forgive. German engineers had pursued excellence in individual components and achieved that excellence repeatedly. But individual excellence in a system that cannot be replicated at scale is a tactical victory that guarantees strategic defeat. The Americans understood something fundamental. In industrial war, quantity has a quality all its own. And when you can combine quantity with good enough quality, you create a compound advantage that technically superior adversaries simply cannot overcome. That's the truth those German engineers confronted in that room, examining that P-47 cockpit. Not that their own designs were inadequate, not that they lacked talent or dedication, but that they had optimized for a different game than the one the Americans were playing. And by the rules of the American game mass production, global logistics, pragmatic engineering, Germany could never compete. So when you hear the story of German engineers examining a captured P-47 and realizing they could never match America, now you understand the full depth of that realization. It wasn't about a specific component. It wasn't about turbocharger or armor or engine power. It was about an entire philosophy of how engineering, industry, and strategy intertwine. It was the understanding that they had built masterpieces for a museum, while the Americans built tools to win a war. And that distinction between artisanal excellence and industrial effectiveness wasn't just relevant for 1943. It's a lesson that resonates in every large-scale engineering challenge humanity faces. When you build something to be the absolute best, you often build something that cannot be replicated. When you build something to be good enough at massive scale, you build something that can change the world. The P-47 Thunderbolt changed the world, not because it was perfect, but because it was exactly what was needed, when it was needed, in numbers that made all the difference. And those German engineers, with all their technical genius, saw this with crystal clarity and knew they had been outmatched not in intelligence, but in philosophy. If this story of engineering, strategy, and the unexpected twists of technological history fascinated you as much as it fascinated us to research, leave a like. And if you want to explore more stories where technical decisions shape the fate of nations, there's much more to come, because in the end, history isn't just about who builds the best machine. It's about who understands which machine really matters and how to build it when the world is at stake.